Hello there, and in this video we're going to introduce the topic of convergence of series, and we're going to look at a little bit of an entertaining example, which is to do with the overhangs that we can achieve from simple stacks of blocks. Okay, so we're going to set ourselves a challenge. We're going to try and make a simple tower of bricks, and I've got some Jenga blocks here that we're going to use for this. And we're going to try and achieve as much of an overhang as we can. So let me show you what I mean. So I have on the desk in front of me here just a small collection of Jenga blocks. We're going to make a simple stack of blocks, which just means I'm going to pile them up on top of each other. I'm not using any glue. There's no tricks involved. There's no glue or string or anything. It's simply just the blocks resting on top of one another. And now you might just build them straight up in a straight line like this, but you can also make them make the block kind of lean over a little bit, something like this. And this kind of stack has an overhang to it. So the overhang in a stack of blocks like this, when we say the overhang, what we're going to mean is the horizontal distance from the bottom, from the rightmost edge of the block at the bottom on the floor, all the way out to the edge of the top block. Okay, so this stack that I've constructed here has an overhang of something over 2 centimeters. So if we want to challenge ourselves to make a stack which has as big an overhang as we can produce, and of course the danger is, as you try and get a bigger and bigger overhang, sometimes the whole thing falls down. You've pushed it too far. Now I could sit here for hours stacking these blocks, trying to get as much of an overhang as I could, but so we need some systematic way to approach it. One systematic way we can approach it is as follows. We use a kind of induction process. So we build up and we first get as much of an overhang as we can with the top 2 blocks, and then work down through the stack. So if I just confine myself to just the top block, how much of an overhang can I get by stacking the top block on top of the blocks below? Well, given that these are made of fairly homogeneous material, fairly consistent material throughout, I can get an overhang that's about half the length of the block. If I position it over here, obviously the center of gravity of the top block then is not supported by anything, so it will move, it'll tilt over and fall off. Whereas the reason that this block doesn't fall off is because the center of gravity of the top block, which will be at the halfway point, is supported there. So the biggest overhang I can get with just placing the one block on top of a supporting block is approximately half the length of the block. So it's about there. So where it's positioned there, the center of gravity of the top block is just in a little bit along the block underneath it, so the whole thing is supported and it's pretty stable. If I break the table a bit, it won't fall over. So we can get an overhang of half the width of a block. And now I take the top 2 blocks. So the top 2 blocks are a stable stack. And I now position that top 2 blocks together without changing the position of the top one relative to the second one. I now position the top 2, consider them as a group, and position them with as much of an overhang as possible. Okay. Now, why does this balance? This balances here because the center of gravity of the top 2 blocks, now, is supported by the block below. It's probably just in a little bit from the edge because I don't want it to tip over if I shake the table a bit. Now it's an interesting question, is where exactly is the center of gravity of the top 2 blocks? It'll be somewhere here, probably in the overlap between the top 2 blocks. Now we'll come to that later on I mean, we've found it by rough experimentation here, but we'll analyze the situation in a moment and we'll be able to describe exactly where that center of gravity is. So now I keep repeating this procedure. I now take my top 3 blocks, which constitute a kind of stable stack, and I overhang them by as much as possible. So the top 3 blocks have a center of gravity, which is probably located roughly around here. And I just bring this over, and I try and feel with my fingers when it's about to tip, and then I just push it back a little bit so that it'll be safe. So I can get to about here. Okay. Again, this stack of those top 3 blocks, the reason it isn't all tipping over is because the center of gravity of those top 3 blocks is itself supported by the 4th block from the top. So I repeat this procedure. I now move the top 4 blocks. Hopefully the thing won't fall over at any point. I position the top 4 blocks just before where they begin to tip over. Flip. Okay, let me quickly get back to the point where I was. I should be conservative and not try and get as much out of it as I can each time. Maybe just go, okay, I'll try and be conservative this time and not push it to the limit. It's not going very well. Okay, start again, super conservative. So close to halfway with the top one. Not too far with the next one. I'm blocking most of the construction with my hand, sorry. Nearly went there. Okay. Let's make this one count. Super conservative. I won't try and push it too much. Okay, I'm doing the last stage now. Okay. There we go. Okay, so I've tried to not push it to squeeze as much of an overhang out of this as I can, but I'm fairly close to the optimum overhang from this particular method of achieving an overhang. Now, even with this small number of blocks, how many blocks do we have? 1, 2, 3, 4, 5, 6. We have 6 blocks here stacked on top of the 7th supporting block at the middle, at the bottom, and we've achieved quite an overhang. Actually, if you look at it, if I position my ruler just right in behind the block here, so my ruler there is showing just at the edge of the bottom block, and you can see here that it's as you're looking at it, it's to the left of the top block. So this means if you look at how much overhang I've got here, actually the total overhang I've achieved here is longer than the width of one of my Jenga blocks. And it looks somewhat paradoxical that the top block is kind of levitating out here in space, and it's completely outside. If you look at if you were to project the top block straight down, it would be lying outside of the support of the bottom block. That looks quite curious. Parts of your mind might tell you that that's not possible. Surely the top block, if you looked at where it's supported on the ground, it must be supported by the bottom block to some extent. But it's not. I mean, if the reason the top block doesn't tip over is because its center of gravity is supported by the 2nd block down. The reason the top 2 blocks don't tip over is because their center of gravity, as a group of the top 2 blocks, their center of gravity is supported by the 3rd block, and so on and so on. Each stack of blocks, each intermediate stack of blocks, their center of gravity is supported by the block that they're sitting on. And so the whole stack is stable, and this increasing amount of overhang each time, I've been able to overhang by an amount greater than the width of one of the blocks. So the question is, if I kept going, I mean, I've got a whole stack of a load more Jenga blocks here. How much of an overhang could I produce with this process? And if I got loads of packets of Jenga blocks, and I got hundreds and thousands of these blocks, so I'm going to go through my ceiling at some point. But in principle, how much of an overhang could we achieve from this? Okay, so I've got a bunch of slides here that analyzes this problem mathematically and gives us the answer to that question. So, a few principles from what we described there. So one principle we use, and these I guess come from physics or that, so a body is going to balance on a flat surface if its center of gravity lies over the footprint. We've been using that principle repeatedly. We're going to be able to determine the horizontal location of a stack center of gravity by averaging over the locations of the centers of the blocks, okay? Because the center of gravity of a single block, center of gravity of a single one of these Jenga blocks is located at exactly the halfway point horizontally, assuming that the material is of consistent density through the block. And the method we've been describing here is we build by adding to the bottom of the pile at each stage. And when adding a block, we position its edge directly under the center of gravity of the existing stack. Okay, that was the principle I was using there as I gradually made my stack of blocks higher and higher. So here's a diagram of my stack. We're going to measure the overhang from the rightmost edge of the top stack. We're going to measure backwards. So we're letting W here be the width of these Jenga blocks. And Hn is going to denote the overhang that we get from a stack of n blocks. And so by applying these principles we described on the previous slide, the overhang you get from n blocks is equal to the horizontal location of the center of gravity of the upper n-1 blocks. So if we imagine there's n blocks in this diagram in total, then in this upper stack here there's n-1. And when I add them onto the nth block below, in order to get the thing to not fall over, I'm going to want to locate the center of gravity of these upper blocks, which will be somewhere about roughly here, where the mouse is. I want to position that center of gravity so that it lies just at the edge of the bottom block. And in that way, the whole thing won't tip over. It'll be supported. Okay. So what is this quantity Hn? Well, we can define a recurrence relation for it. The overhang you can achieve with just a single block is of course 0. I mean, if I just have a single block, I just set it on the ground like that and there's no overhang at all, okay? It's just a block sitting on the ground. So the initial value, H1, is 0. And then what we've just been describing there is that the overhang we get from a collection of n blocks, it's going to be the overhang you would get from a collection of n-1 blocks. So from a collection of n-1 blocks, so that would be referring here to the top 4 blocks. The overhang you get from them is about here, and it's the point at where the 5th block comes in. So that overhang you get from, which is effectively from the top n-2 blocks, that's the overhang Hn-1. And then we get a little bit more because we add on this n-1th block to the bottom. And its individual center of gravity is located halfway along its distance. But it is only one of n-1 blocks here. So we need to average it, and it only carries a weight. So the location of the center of gravity of the n-1th block, which is the one just above the bottom block here, its position of gravity is halfway along its width, but it is only one of n-1 blocks, so it gets a weighted contribution. That W over 2, the increase to the center of gravity given by this next block, it has to be weighted by 1 over n-1, okay, in order to calculate the location of the center of gravity of the top stack of n-1 blocks. So by applying these kind of physics principles, we can achieve this nice recurrence relation for the overhang Hn. Okay, let's develop this recurrence relation. Let's just look at the values that come out of it. H1 is 0 by definition. H2 is going to be W over 2. H3 will be W over 2 plus 1/2 of W over 2. So that's 1.5 times W over 2. H4 will be W over 2 times 1.5, that's the previous value, plus 1/3 of W over 2. So we can factor out the W of 2 again, we get 1 plus 1/2 plus 1/3. That's the overhang for H4. You keep going in this way and you can write down, but you can see the pattern that's happening. The overhang coming from a stack of n blocks is going to be W over 2 times 1 plus 1/2 plus 1/3 plus all the way to 1 over n minus 1. Now what you see here is the development of an important series in mathematics, which we'll say more about as we go through this section, but this is known as the harmonic series. Okay, I'll explain why it has that name in the next video when we're considering it, but it's known as the harmonic series. So what we're seeing here is the first few terms of the harmonic series. So how much of an overhang can I get? In the demo we just did, we achieved an overhang of more than W. W is the width of one of these blocks, so even with this small number of blocks, we've been able to achieve an overhang of greater than W. But if I had as many blocks as I needed, as I cared for, what kind of an overhang could I achieve? Well, in fact, one can prove that this series, it's clearly an increasing series. It's getting bigger each time, but it's getting bigger and bigger by a smaller amount, because these fractions, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, and so on, they're of course getting smaller and smaller. However, they will still increase without any upper bound. Okay, so I can give a proof of this here. So we're thinking of this series, maybe thinking of getting as many terms as you want into it, so maybe thinking about the infinite series. We can prove that this actually diverges, that it will grow to be bigger than any amount. And the way we do it is we group the terms in a certain way. So we have the first two terms, 1 and 1/2, we leave them alone. Then we group the next two together, 1/3 plus 1/4. Then we group the next 4 together, 1/5, 1/6, 1/7, and 1/8. Then we group the next 8 terms together, 1/9, 1/10, etc., all the way to 1 over 16. We keep repeating this process. We're going to double the size of the group at each stage. So the first group had size 2, the next group is size 4, the next group is size 8, the next group will have size 16. It'll go from 1/17th all the way to 1/32nd, and so on and so on. Now leave the 1.5 alone. And then in each group, you can replace all the terms in the group by the smallest last term. So 1/3 plus 1/4, that's going to be bigger than 2/4, okay, because 1/3 is bigger than 1/4. And in the next group, you have 5th, the 6th, the 7th, and 8th, we can say that that is going to be bigger than 4/8. Okay, replace the 5th, the 6th, the 7th with 1 over 8. Each of those fractions, the 5th, the 6th, the 7th, is bigger than an 8th. So this group, whatever it is, from 1/5 to 1/8, it's certainly bigger than 4/8. And the next group we can say is bigger than 8/16, and so on and so on. Now, of course, these quantities are just 1/2, 1/2, 1/2, 1/2. 8/16, 16 32nds, 32 64ths, 64 128ths, etc., etc. So what we seem to be saying is that the whole infinite series is strictly bigger than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, and the halves never stop, okay? By each new group of terms in the harmonic series will generate another 1/2. And we need to take more and more elements into the group at each stage, sure enough. But if I have as many blocks as I need, as I care for, I can generate as many halves into this expression as I want. So if I have as many blocks as I need, I can grow this factor here to any size that I wish. So in principle, we seem to be saying that we can get any overhang we desire whatsoever. Now remember here we have an overhang of something over W, a little bit over W. And what this analysis seems to be saying is that if I keep adding blocks in at the bottom here, I can grow the overhang and I'll see it become bigger than any specified value, which seems quite a curious conclusion. Now let's just do a little thought experiment here. Let's actually try and, sorry, we're not ready for the thought experiment yet. We're going to do a little bit more analysis. Let's try and quantify, or let's try and describe the size of this factor a little bit more. And we can do so by comparing it to an integral. We're going to see this idea come up later on in the chapter of comparing the sum of a series to the value of an integral. So in red here, I have rectangles whose area is equal to each of these terms in the series. So I have a rectangle of area 1. It's got width 1 at the bottom and it's got height 1. I've got a rectangle of area half because it's got width 1 and height 0.5. Then I've got a rectangle of area third, then one of area quarter, and so on and so on. This blue curve here is the curve of the graph of 1 over x. And adding up 1 plus a half plus a third all the way to 1 over n minus 1, you can see from the graph that it's approximately equal to the integral of the function 1 over x from 1 up to n. Okay, because this last block extends from n minus 1 on the left edge to n on the right edge. So approximately the size of Hn is w over 2 times the area under the blue graph between 1 and n. So that's the integral of 1 over x from 1 to n. Now I say approximately equal to. Of course, it's not exactly equal to, because there are these errors here. These gray quantities aren't counted for by the integral, okay? Because the integral of 1 over x from 1 to n gives you the area lying underneath the curve. Now that's most of the area in the red triangles. But we've missed out the area protruded in each rectangle that protrudes above the graph. There's a fair chunk in the first one, but in subsequent rectangles you get less and less of a contribution there. So we could say the overhang from n blocks is going to be, oh, I've missed out my factor. Oh, there's a little bit of a misprint here. I've missed out my factor w over 2. So there should be this w over 2 in front of the integral there, but never mind. So this hn should be w over 2 multiplied by, and now I can make it exact by saying that it's the integral from 1 over x to of 1 over x from 1 to n with respect to x plus gamma n. So gamma n I'm defining as the sum of the area of these shaded regions up to the nth block. Or the n minus 1th block, maybe. Now the thing about gamma n is, in the limit, it's actually a finite number, because all these extra gray regions protruding above the graph 1 over x, if you actually imagine sliding them all, parallel transporting them all to the left, they'll all fit inside this first block. And they don't overlap with one another, okay, because the curve 1 over x is strictly decreasing. So you get that this infinite number of these gray errors, they actually all fit inside the first block. So the limit of them, the limit of the total gray area is going to be something less than 1. Turns out it's got a value that's approximately 0.6. Okay, the limit of these sequences of these accumulated gray errors. It's quite a famous number in number theory and in mathematics. It's called the Euler-Mascheroni constant, and its approximate value is 0.6. It's an example of an irrational number, but it's approximately 0.6. So here I've corrected myself now. Here the factor w over 2 comes back in. So the summary of this then is that for very large n, a very good approximation to the overhang is going to be w over 2 times this integral plus 0.6. So the error now in this approximation is the difference between the true value of the Euler-Mascheroni constant and this approximate value is 0.6. But just to simplify it, we'll just work with the approximation 0.6. Now, of course, what is the integral of 1 over x dx from 1 to n? Well, it turns out that that's the logarithm of n. Okay, it's the natural logarithm of the top limit to n. So this finally gives us something that we can calculate with easily now. We can use our calculators or computers to compute pretty good approximations to these overhangs. Now, as I keep saying, our demo block here of 7 or 8 blocks, however many we have here, got an overhang of just over W. Our argument has shown that in principle we should be able to achieve any overhang whatsoever. So let's set ourselves a little challenge. Can I build, or what kind of stack like this, like the demo one we built, what kind of stack would have a 3 meter overhang? Now, these Jenga blocks, they're 7.5 centimeters wide. Okay, the distance between my fingers there, and they're 1.5 centimeters tall. Okay, so the height of them, just this distance, is 1.5 centimeters approximately. So if we feed these numbers into this formula, if I want an overhang of 3 meters, it's going to be given by this formula here. So I'll need n blocks, and I replace the w with 0.075. So that's my 7.5 centimeters expressed in meters. So this gives us an equation for n, which we can solve. Okay, so you just make n the subject of this. You just peel off the various operations there, and eventually you'll have to take the exponential to invert the logarithm. So you take the exponential of this quantity, 3 divided by 0.0375 minus 0.6. If you actually work this out, you see you're going to be taking the exponential of quite a large number here. Okay, because we're dividing 3 by 0.0375. 0.0375 is half of 0.075. This will work out as approximately 3 times 10 to the 34. Now n is the number of these Jenga blocks I need. So we seem to be saying that we need approximately 3 times 10 to the 34 of these Jenga blocks to build a stack like we have been doing and achieve an overhang of 3 meters. Now 3 by 10 to the 34 is a big number. It's a 3 with 34 zeros after it. Each of these blocks, remember, is 1.5 centimeters tall. So we can work out how high that stack of blocks would be. It would be 3 by 10 to the 34 by 1.5 centimeters, which is 0.015 meters. So it's approximately 4.6 by 10 to the 32 meters tall. So sorry, just got disturbed there. So it's going to be quite tall. 4.6 by 10 to the 32 meters tall. This is quite a stack of blocks, surely. Yeah, it's going to be well taller than my little stack of 7 blocks there that we have. Yeah, 4.6 by 10 to the 32 meters tall. That's very tall indeed. Okay, it's approximately 520,000 times the diameter of, well, at least of the observable universe. Okay, our estimates of the diameter of what we can see of the region that we can observe in the night sky, this number 4.6 by 10 to 32 meters is a huge multiple of that, 520,000 times that approximately. So we can build a stack of blocks with a 3 meter overhang, but it would have to be extremely, extremely tall. So I hope you enjoyed that. The purpose of that, well, aside to discover this kind of interesting phenomenon of overhangs from stacks of blocks, but it showed us a important phenomenon of divergence of an infinite series. This infinite series called the harmonic series. So this notion of when an infinite series converges, when it diverges, is what we're going to be studying in this second chapter on series. So See you in the next videos where we're going to develop our mathematical theory of all this.